Good day to you. In this chapter, what we're going to be looking at is we're going to be looking at magnetism. All right. So let's start with doing a few problems here. Actually, we're going to do a whole lot of problems. It may be broken up into a couple videos. The first question reads, an electron moves at a speed of 6.0 times 10 to the 6 meters per second to the right. Remember, I'm going to be a mirror image of what you folks are seeing, okay? So you have to remember that. A magnetic field of 1.5 Tesla points straight up. All right. What is the magnitude of the force on the electron and its acceleration? So we need to look for the force in this case. So the equation that we're going to be using is that force of the magnetic field is equal to the charge times the velocity times the magnetic field sine of theta, where the sine of theta is going to be the angle between the B field and the velocity, or the direction in which the particle is moving. Now, in our case, sine of theta is going to be equal to 1, and that's because theta is equal to 90 degrees. All right? So our equation becomes QVB. All right? Now recall that the charge of an electron is going to be equal to 1.6 times 10 to the negative 19th coulombs. The velocity is 6.0 times 10 to the 6th meters per second times, now the magnitude of the B field, which is 1.5 Tesla. We go through and do this arithmetic, what we end up getting is we get 1.44 times 10 to the negative 12th newtons. So that answers A. Now for B, this is going to be kind of hard. You're going to have to get some orientation on. You're going to have to practice this on your own. B says, what is the direction of the force? So what is the direction of the force? You're going to have to use the right-hand rule for this. So you're going to have to right cross up out of the page, but you have a negative because of the charge of the electron, and so this is going to go into the page. We have another question now in this case, or another problem in this case, where we're dealing with the electron once again traveling at 6 times 10 to the 6 meters per second to the right. So let's go through the question yet again. An electron moves at a speed of 6 times 10 to the 6 meters per second to the right. A magnitude field, or a magnetic field, points into the page, and the electron follows a circular path of radius 1.3 millimeters. So the radius is going to be 1.3 millimeters. All right, we'll get with that in a little bit. I was getting ahead of myself, sorry. Which direction does the electron circulate? Find the magnitude of the magnetic field. And C, find the magnitude of the acceleration. All right. So for the first part, it says, which direction does the electron circulate? So you want to have her palm up. Now remember, you're going to have to use your right hand for this. Mine, I'm doing a lot of things with this image, so it's flipping back and forth. I write with my left hand, okay? So just understand that. You want the palm up because that's the direction in which the force is up. You want to curl your fingers up, and as you curl those fingers up, right, as you curl those fingers up, you see that it's going clockwise. It's going clockwise, all right? And so in A, which direction does the electron circulate? And that's going to be clockwise. It's going to be clockwise. B says, find the magnitude of the magnetic field. In order to find the magnitude of the magnetic field, we are going to use the equation that B is equal to mass times velocity all upon the charge times the radius. Now remember, the radius in this case was given 1.3 millimeters, so this is equal to 1.3 times 10 to the negative 3rd meters. Okay? If we solve this, or if we start plugging in our numbers into this, we know that the mass of an electron is going to be equal to 9.1 times 10 to the negative 31st kilograms times 6 times 10 to the negative 6, positive 6 meters per second, divided by now the charge of an electron, which is going to be 1.6 times 10 to the negative 19th coulombs, times the radius, and that's 1.3 times 10 to the negative 3 meters. If we go through and do the arithmetic here very quickly, we end up with 2.6 times 10 to the negative 2 Tesla. Oops, not B. We're going to do C. Let me get this erased. C states find the magnitude of the acceleration. Now remember that our force is equal to our QVB sine theta, but once again our theta is equal to 90, so this whole term goes to 1. And what our force becomes equal to, I'm just going to erase this real quick. What this becomes equal to now is our charge is 1.6 times 10 to the negative 19th coulombs times our velocity, and our velocity is 6 times 10 to the 6 meters per second times the B field, which we just found, which is 2.6 times 10 to the negative 2nd Tesla. If we do this arithmetic very quickly, this becomes equal to 2.52 times 10 to the negative 14th newtons. That's our force. But we have to remember that force is equal to mass times acceleration, and so our force here, we can use now our acceleration is equal to force all over the mass. We just found the force is 2.52 times 10 to the negative 14th newtons divided by the mass of our electron, which is 9.1 times 10 to the negative 31 kilograms. We do this arithmetic very quickly. We end up getting 2.8 times 10 to the 16th meters per second squared. And so now that is going to be the acceleration of the electron. All right, for this next problem, what we have is we're going to be mixing magnetic fields and electric fields together. So the question reads as such. A magnetic field has a magnitude of 1.2 times 10 to the minus 3rd Tesla. We have that. And an electric field points in the same direction, or an electric field has a magnitude of 4.6 times 10 to the 3rd newtons per coulomb. Both fields point in the same direction. A positive 1.8 microcoulomb charge moves at a speed of 3.1 times 10 to the 6 meters per second in a direction as perpendicular to both fields. Determine the magnitude of the net force that acts on the charge. So what we're first going to do is we're going to say, well, we have this electric field, so there's an electric field that points in one direction. Now the direction of the force from the electric field is in the exact same direction as that. Okay? Now if we look at, oops, wrong one. I'm sorry, I got ahead of myself again. If we look at the magnetic field is going to point parallel to that of the electric field. So it's going to point parallel to the electric field. Now we'll get to the direction of the force due to the magnetic field in a few minutes. The velocity vector is perpendicular to both the electric field and the magnetic field, and that's going to be how we're going to represent that. Now let's deal with the force on the magnetic, or as a result of the magnetic field. What you're going to do is you're going to take your fingers, hopefully, preferably it's going to be on your right hand. This is my right hand. It may appear as my left hand, but this is going to be my right hand. I write with my left. You're going to point your fingers in the direction of the B field, and your thumb is going to represent the direction of the velocity vector. Your palm is going to represent the force due to the magnetic field. And since it's coming out at you, you're going to draw that as a dot. So this is going to be the force due to the magnetic field. If it were going away from you, this would then be an X. Okay, so that's how you get the distinction of the direction of all the different forces. Should put my vector up there. Now, if we look at the force due to the electric field, we saw that a few chapters ago. The force due to the electric field is going to be equal to the charge times the magnitude of the electric field. And so our charge is going to be 1.8 times 10 to the negative 6 coulombs times now the electric field, which is 4.6 times 10 to the third newtons per coulomb. We do this quick arithmetic, and what we get is we get 8.28 times 10 to the negative third newtons. Now, if we look at the force on the magnetic field, that's going to be QVB sine of theta. Once again, our sine of theta is going to be 1 because in this case, the angle between the magnetic field and the velocity vector is going to be 90 degrees, and the sine of 90 is going to be 1. And so this is QVB. We put the numbers in here, so this is 1.8 times 10 to the negative 6 coulombs times our velocity, 3.1 times 10 to the 6 meters per second, times now our B field, which is 1.2 times 10 to the negative third Tesla. And if we do this arithmetic, what we end up getting is we get 6.7 times 10 to the minus 3 newtons. All right. Now, if we want to find the net force, we have to use the Pythagorean theorem. And so the net force is equal to the square root of the electric field plus, or the square of the electric field plus the force of the magnetic field, the square root of those two. We plug those numbers in, and we end up getting 0.01 newtons. All right? I think the hardest thing on this problem is figuring out the direction of the force due to the B field. And just remember, your fingers on your right-hand side are going to represent the direction of the B field. The thumb is going to be the velocity. And in the palm, your palm is going to be the direction in which the force of the magnetic field is going to be. If the velocity vector were going the other direction, it would go out towards you. All right? In the previous example, what we did is we looked at a particle that was moving in a particular direction to that of the electric field and the magnetic field. All right, so it was just an individual particle. In this problem, what we're going to be looking at is a large amount of particles moving in a direction. That's going to be because we have a conducting wire that has a current of 23 amps. All right, so let's read the problem. The problem reads as such. A wire of length 0.675 meters carries a current of 23 amperes in the presence of 0.495 Tesla in a magnetic field. The wire experiences a force of 5.55 newtons. What angle between the wire and what is the angle between the wire and the magnetic field? So if we look, we have the following equation. So we can say that our force is equal to our current times the length of wire times the magnetic field times the sine of theta. In the angle is going to be between the magnetic field and the conducting wire. Remember, your fingers on your right hand side are going to point in the direction of the magnetic field. your thumb is going to point in the direction of the current or the charge that's being carried, and your palm is going to be the force or the direction of the force of the magnetic field. All right? So we have this equation here. This is going to be a magnetic force, not an electric force. It's going to be a magnetic force. We're looking for theta, so we can solve this for the sine of theta is equal to the force divided by the current times the length of the wire times the magnetic field. And so this is going to be equal to 5.55 newtons divided by the current, which is 23.0 amperes, times the length of the wire, which is 0.675 meters, times the B field, or the magnetic field, which is 0.495 Tesla. All right? We go through and do this arithmetic, we find out that the sine of theta is equal to 0.7222. All right? We do the inverse, so our theta is equal to the inverse sine of 0.7222, and that is equal to 46.2 degrees. So the angle between the B field and the charge, or the current, is going to be 46.2 degrees. Okay?